Yeah, thanks for the introduction, and thanks a lot for inviting me here. I was very happy about this, and thanks to the organizers for giving us early career researchers such a great opportunity to do this. I think that's really great and worth mentioning. So so the title of my talk. So the question that I want to address here is, what are good reduction procedures in proofs, and why does this question matter? And you can say in the lines of Doug Pravitz or Pierre-Martin Loew, or many others have followed them in this, so that this is a question that is important for the question about identity of proofs. So the idea is, if you you can say that one same proof may be, of course, linguistically represented by different derivations, and the proofs are identical if they're equivalent. And since reduction procedures can be seen to induce an equivalence relation, then you can say that proofs related via these reductions are identical in nature. However, it has been argued that there are more reduction procedures than our standard ones, the ones for the connectives that have been introduced by Pravitz, etc. So Ekman or Newton, for example, argued in this direction. And to give an example here of one that we will call Ekman-reduction, is that, we can have, for example, such a derivation. We have a derivation of A, and then we assume A implies B. And from this we can go to B, and we also assume B implies A. From this we get A. Okay, then we can reduce this to this derivation of A, which we had in the beginning. This reduction has been examined and then ultimately rejected in a paper by Peter Schröder-Heister and Luca Tranchini, which is called Ekman's paradox. So they consider this in this context of paradoxes. I will not go into detail about this here, but their line of argumentation is that accepting Ekman reduction basically would trivialize our notion of identity of proofs. Accepting Ekman reduction would lead to a failure of the George-Rosa property, meaning that we could have two different derivations in normal form obtained by reducing one derivation. And they show that then every derivation of the same conclusion would ultimately have to be identified. So there couldn't be two non-identical proofs of one formula, which is, of course, very unintuitive, very undesirable. We want to be able to say that a formula can have different proofs made. So they proposed this as a criterion for accepting reductions, so that they must not trivialize this notion of identity of proofs. And what I want to show here is that there's something else wrong with Ekman reduction that makes it unacceptable, even if we do not accept such a theory of proof identity. Because, there are some people, like, for example, Tennant, who would be hesitant about this theory of proof identity, would just say, well, that's not a good theory. But I want to show that accepting Ekman reduction would actually mean, would lead to rendering proofs containing this meaningless, which is even worse. So method here is I'm exploiting the Curry-Howard correspondence, and I want to consider here term-annotated proof systems in Curry style. And then the question shifts a bit to which reduction procedures for terms can be allowed then. And the advantages of this method, I think, is that we can use the lambda calculus and some well-established and well-known properties thereof. We can use this to let us guide the direction what are maybe good or maybe not so good reductions. And also it makes the structure of derivations explicit. So it shows differences between derivations, which would otherwise look the same. And if one is not only interested in just provability, but also wants to study the structure of derivations in question, then this is a useful tool, I think. So this is my outline, the introduction. We just had, and then I will say a few words on reduction procedures in natural reduction and lambda calculus. And then I will come to the main question, what could be criteria for good reductions? And my way of proceeding, I want to show an example of a reduction, of a tonk reduction, like an example of a reduction which is definitely not acceptable, and then show with these features of subject reduction and type reconstruction which features Ekman reduction and tonk reduction share, and then argue that these features would render derivations meaningless in a system allowing them. And if we have time, we'll have to see how I'm doing in time, then we can discuss some possible objections and answers. Otherwise, I will jump right ahead to the conclusion. So reduction procedures in natural reduction, how are they usually constructed? Usually they're meant to eliminate an unnecessary detour of a specific form, namely eliminating maximal formulas, which are like both conclusion of an introduction rule of a connective as well as major premise of an elimination rule governing the same connective. And for the standard connective, it can be shown then that maximal formulas can be eliminated without losing anything essential, because as Pravitz argues, reductions are simply a way of making the inversion principle explicit. So the inversion principle telling us that nothing new is obtained by applying an elimination rule immediately after an introduction rule, basically. And here you can see the well-known reduction procedure for implication. I will just consider implication fragment here of intuitionistic logic, because that's enough for our purposes. And in term-annotated form, this would look like the following. So we have lambda abstraction here and function application for the elimination rule. And this would be a non-normal term, the result of applying an implication introduction rule and then elimination rule. And we can, the beta reduction would be like this. So in term T, every free occurrence of X is substituted by S. And we call this the redex and this the contractum. And we say that a term is in beta normal form if that term contains no beta redexes. And we read this T colon A as a term T is of type A, or in the proofreading, T as a proof of formula A. I'm hearing some noise. I'm not sure where this is coming from. Am I the only one hearing this? I don't know. Okay, sorry. So yeah, x, y, z for term variables, which I used for assumptions in natural reduction, and here as for arbitrary terms. And this statement is also called a type assignment formula, the term being the subject and the type the predicate. And by this you can already see that I'm working here in a type system a la Curry, because the terms are not typed as in church style, like that the type is part of the term structure, but they are assigned by it according to typing rules. So yeah, now to the question, what could be criteria for good reductions? Then I told you in the beginning, I want to start with an example of unacceptable reduction. So the question is, okay, can there be a reduction for tonk? And well, briefly recap on what tonk is, although I'm very sure with this audience that everyone knows. But with tonk, we have these introduction rule of from A, we go to A tonk B, and from A tonk B to B. And why is this bad or bad connective? Well, of course, because it trivializes our consequence relation. We can derive everything from anything, basically. And yeah, this is because, I mean, tonk does not adhere to this inversion principle. And so there can no reasonable reduction procedure can be given for this. And maybe it's worth emphasizing that, I mean, there are people like Dave or Roy Cook who argued that, given certain assumptions, maybe tonk is not like itself unacceptable. It does not necessarily lead to inconsistency, but still, I mean, at least I haven't seen anyone arguing for the fact that that tonk has a reasonable reduction procedure, that you can give a reduction procedure for tonk. Is still then a different question. So what would this look like in a term annotated setting? How does it like work for terms in general to give a reduction procedure? Well, in general, that's a simplified version of this procedure, but in general, you get a non-normal term. So a non-normal term consists of like a destructor to call C prime applied to a constructor, the constructor decorating the introduction rule and the destructor the elimination rule, and the constructor which is applied to the term of a premise of the introduction rule. So we convert, and the reduction is then to convert this term, this would be the non-normal term coming out of this C prime CT, to T again. An example here for a non-standard connective, which is from Peter Schröder-Heister, where he gives this for a liar constant. So for a constant saying about itself that it implies absurdity. Okay, we can have this introduction rule for the liar, and here L is our constructor, so this decorates the introduction rule, and we have an elimination rule for the constant, and this is decorated by the L prime. And then we have a non-normal derivation then here, where we build up this non-normal term, which is then L prime LT. And we can see here, okay, we can have this reduction, and it makes sense here. It looks fine. Why can't we do the same for tonk then? Why can we use now K and K prime as the terms, as a constructor and destructors? Why can't we say that K prime KT reduces to T in just the way that it worked for the liar? And the thing is, you can see this here. If the way to get a non-normal term be this, okay, and then we would have to reduce this term of type B to this term of type A. So if we allow this reduction, and we take reductions as identifying the related terms, this would mean to identify a term of an arbitrary type with one of an arbitrary other. So to identify a proof of an arbitrary formula with one of an arbitrary other. And I mean, this seems to me is even worse than identify all proofs of one formula, like what is Peter Schröder and Luca Tranchini showed for what happens if we accept Ekman-reduction, was that then we have to identify all proofs of one formula. Here, this would happen. And I want to show now that what's wrong with Ekman-reduction is essentially the same as in the case of tonk-reduction. So if we look at Ekman-reduction in term-annotated form, this would look like this. So here we have this derivation of A. Now we have an assumption, A implies B. So we have a function application here. Another assumption, B implies A. These are then decorated with the variables, with assumptions. We get another function application. So this would be a term in non-normal form for Ekman reduction. And what we would have to say then is we reduce this to T. Yeah, that was the thought of Ekman reduction. However, this term structure is too unspecific concerning the typing rules, because basically you can, with the same terms, because T is just standing for an arbitrary term, right? You can have this derivation here. So we have this identity function, and we get lambda zz, w implies w. And we have this as an assumption here. And from this, we can go to Q with modus ponens. And this is our other assumption, Q implies P. And from this, we get with modus ponens P again. So this then, a term in non-normal form according to Ekman reduction. And if we apply this to this, then we would have to reduce this to lambda zz. But no type assigned to lambda zz can be atomic. Like from the typing rules, this is an impossible type assignment. And the problems this is related to have to do with type preservation and type reconstruction, which I want to show now. So first of all, I want to talk about subject reduction theorem, which is a very important theorem and important property for reductions to have. So it says that if we have a derivation of term t of type A and t reduces to t prime, then we also must have a derivation of t prime of type A. And this actually holds for beta reductions. This does not hold for tonk and for Ekman reduction. So subject reduction fails here. And to hint a bit at the significance of this type preservation, because subject reduction, as the theorem states, the property of type preservation in reductions. Types are preserved within a reduction. So if we understand types like labels telling us combinations that can safely be made with a term, which is like what the interpretation is in the literature, basically, then subject reduction tells us that terms will not become like less safe during a reduction. So a computation cannot turn terms from well-typed into ill-typed ones. This, like having this property, this establishes the correctness of our system of type assignment, basically. It seems, therefore, that maintaining subject reduction would be a desirable feature for reduction procedures. This seems like something we want to have. However, the question is now, okay, is it a really good criterion to say a reduction is acceptable or not acceptable? So should we, on this basis, say that Ekman reduction is unacceptable because it lacks this feature? And the question now then would be, okay, do non-type preserving reductions necessarily lead to this trivialization of the system? Or are there maybe systems which can contain reduction procedures that are not type preserving but yet do not trivialize proof identity? And this it seems this was pointed out by Dave, especially to me, and also Luca Franchini. So that, okay, failure of subject reduction need not necessarily cause trivialization. It's not impossible that there could be a type theory with a reduction that is not type preserving without relating terms of arbitrary types, but for example, like only of types which are equivalent, interderivable formulas or whatever. And there are examples actually. So Heinrich Wansing propose a type theory for N4, constructive logic of Nelson with strong negation, in which terms of type of a certain type are identified with terms of double strongly negated types. Or Dave has a system, or has given a type theory for Tennant's core logic, so core type theory. Sorry, okay. So in which, okay, what is there happening is, okay, there we have different, we have two rules for implication introduction, and therefore subject reduction fails there too. But it's in a different way. So we have we don't have this complete arbitrariness, but we have basically then two different paths that could the reduction could go, but these paths in themselves, they are very determined. So that's another example where you don't have subject reduction, but not this arbitrariness. So the actual problem, I think, can rather be identified when we look at type reconstruction. So type reconstruction saying is the question, like we have a term t given, and now we want to track down whether there's a context gamma and a type A, such that from this context we can have a derivation of this term t of type A. And for this we use our typing rules, and the typing rules are just syntax oriented. In our case, they're just given by the annotated inference rules of our system. So to give an example here for if we want to do type reconstruction for a non-normal term, resulting from implication, so from the implication rules. This would be a non-normal term here, and okay, we want to do type reconstruction for this, so we assign this just an arbitrary type B. What do we know then? Okay, we know from this that there must be, so here we have to have a lambda abstraction, and here this so we have to have this term S here, which this is applied to. And we know that B must stand in this position, and we know that the question marks must be identical, but otherwise, like, the question marks are not further determined. Okay, so we know that they must be the same, so we assign the question marks, now we call them A. And what do we know further? Then we know from this that X must be of type A and that T must be of type B. So here, this is like very, very determined. There's no other way this type reconstruction could go. And we see here that, this is a safe reduction. T is of the same type as the red X. But now, if we do the same for tonk, for example, take a non-normal term K prime KT. So this was our result of a non-normal derivation with tonk. We assign this an arbitrary type B here. And okay, the only information this gives us for KT is that the type must be of the form question mark tonk B. And okay, now we assign this an arbitrary other type. T can be like any type now. So we have the case here that the types of regex and contractum are completely independent of each other. And the same problem is exists in the case of Ekman-reduction. So we assign this non-normal term resulting from Ekman, this Ekman derivation, an arbitrary type A. Then all we know is that A must be in this position and that the question marks must match. So we assign the question marks another type. We say that they are B. Then we know that B must be in this position and that the question marks must match again, but the question marks can be now any type. They don't have to be A. It's nothing like dictates us that in the type reconstruction. So we can have C here for the question marks. So again, the types of regex and contractum are completely independent of each other. This allows us reducing a term of one type to one of an arbitrary other. Yeah, and the thing is, like, this arbitrariness cannot arise with the beta reductions. The typing rules just determine this in a way that make it impossible. And this is not only to say like beta reductions are great and everything else is not, but also if we would look at the Liar constant again, the rules I showed you for this would be also absolutely fine. The rules determine it in a way that there cannot be anything else happening there in type reconstruction. Yes, okay. So what I'm proposing now is to demand something I will call weak subject reduction. I mean, that was a suggestion by Luca to call it like this. I hope this term doesn't already exist for something else. So weak subject reduction, meaning that it cannot be the case that if we have a derivation of term T of type A and T reduces to another term, then we have a derivation of this other term of type B for every B, basically. So that this cannot happen. And the thing now is, okay, we demand this for good reduction procedures. Yeah, for reduction to be acceptable in our system, it should enjoy a weak subject reduction. And the way to check this then is to build a type reconstruction for a term that would count as non-normal under this reduction, and choosing arbitrarily different types whenever the typing rules allow this. And then if the types of regex and contractum occurring in this reduction are of arbitrarily different, unrelated types, then weak subject reduction fails. And then this reduction should be rejected. I'm just, stressing this way to check this because I think this is a very easy way to check this. And as opposed to like in the paper by Schröder, Hester, and Tranchini, I mean, they showed in a very, very clever way that like what happens if you accept Ekman-reduction and this trivialization of proof identity. But it's also, it's a fairly complicated way. And yeah, I mean, you have to think of these examples. They do this in a marvelous way, but I think this is very advantageous that this is quite easy to do this. Yeah, and like to stress this again, what's the problem here? So if we consider reductions to induce identity of proofs, then this arbitrariness occurring, this would be certainly undesirable. Like then you would have to identify proofs of different arbitrary formulas. However, like I said in the beginning, there's no necessity to subscribe to this identity theory of proofs. You can have another conception of reduction, so not seeing them as like this equivalence relation, but see them in a directed way. So as calculations, that's often said, or evaluations, interpretations of a program. So only as one direction and not this identity relation between what they are relating. And what I want to stay now is that still, if you see them like this, still this arbitrary type reconstruction is problematic. So it's not only problematic for the identity of proofs, which we could now to switch to a philosophical mindset and say that this would be the denotation, but also for the sense of proofs. Okay, and I want to try to briefly tell you what I'm having in mind when talking about this sense and denotation of proofs. So this has been also done by Luca Tranchini. He argued for this kind of Phrygian distinction in the following line, saying that proof objects are the denotation of derivations represented by derivations in normal form, because this is like the most direct way of representation of proofs. And because the reductions are the instructions telling us how to get to this normal form, we can say that it is a necessary condition for derivations to have sense, to contain only rules which have reductions available. So basically, by this, he said he excluded something like tonk, because tonk has no reduction, saying like, okay, if something contains tonk, then this derivation doesn't have sense. I agree with this. I just try to extend this notion of sense but in linking it to the way derivations are built up. So to give you in a nutshell, what I'm arguing for there is that the denotation of derivations, and I'm working in this other paper also with the term-annotated system. So saying that the denotation of derivations would be then represented by the end term in normal form. So the end term decorating the conclusion of a derivation. And then if we look into the literature, like how has Phrygian sense been characterized, it's been said that it's a procedure to determine denotation, a sequence of instructions. So I was thinking, okay, then the sense of derivations consists of the terms occurring within the derivation, because they determine basically how the end term is built up. They form in a way a sequence of instructions on how to operate on the terms. You can in a way like read off these terms, like what is going on, what operations are made in order to get to the end term. And then in such a system we can have now an analogy to Frege's cases. We can have different syntactical derivations, so different signs in Frege's language, but the same sense, if the way of inference is essentially the same. I think I have an example of this here. So different syntax but same sense would look like this. Here, I mean, I would say, these derivations have the same sense because, I mean, the terms occurring in them are exactly the same. They just differ in the, like, different variables are chosen, but that doesn't really matter. That doesn't change the sense, the way the inference is built up or anything. To give a more complex example, here we would have a derivation of the same formula in natural reduction and in sequence calculus. And here again, the terms occurring here, they're exactly the same. So the operations that are made, whether it's in natural reduction or in sequence calculus, are the same operations. We just, I mean, it's just written down in a different way, but what essentially happens is the same. Yeah, and to go back, oh, no, sorry. Oh yeah, okay, the other case is we can have now Frege's famous morning star, evening star example. We can have different senses too, but the same denotation. When the underlying proof is the same, but it's reached in different ways. So the example here is, yeah, you have this derivation, and this is just one in non-normal form where you go through this unnecessary detour, conjunction, introduction, elimination. So you get a non-normal term, which can be reduced just to this term. So you could say, okay, same denotation, because same n term in normal form, but yeah, the way the inference is built up is different, so the sense differs. And the same you can get for sequence calculus with derivations containing cut or cut-free ones. So the idea is here, okay, whether or not we endorse a reduction theory of proof identity, or we say, no, we don't want to accept this, we see reductions as calculations. Still, the notion of sense fits both conceptions. Of course, the denotations would then differ, because in the one case you identify certain proofs, which you in the other case don't. But still, it must be the case that the sense determines the reference. So this is important. And also the syntax determines the sense. These things are important for Frege. You cannot have like one sign, but then different senses, for example. However, I mean, this only works if the rules determine the type reconstruction to a necessary extent. Otherwise, it cannot be said, if we have this arbitrariness, we cannot say that the syntax really determines the sense. But meaning must be in some way, it must be rule governed. So it cannot be like generated completely arbitrary. So yeah, in such a system, so it makes sense to disallow, even if you say reduction is not as generating proof identity, it makes sense to disallow reductions which render our meaning, our system meaningless in such a way. Okay, so I have a bit of time for, yes, I have time for possible objections and answers. So an objection that has been raised in like talks and communication was to say, okay, this term-annotated Ekman-reduction is actually, seems like an inadmissible generalization of the original Ekman-reduction, because in the original reduction, it was clearly like it was essential that you have this A implies B and B implies A as assumptions, and not like any kind of implication. So we could say we just need some restrictions on the type. So we can say that this Ekman reduction only goes through if yeah, regex and contractum are of the same type. Okay, I mean, in the same way, we could restore tonk-reduction and say that tonk-reduction is fine if and only if k prime kt and t are of the same type, which would amount to say, if we have A and we go to A tonk A, and from this to A, then we can reduce it to A. Sure, we can say this, but it seems to me that, I mean, this is not really what we're interested in when we talk about what are acceptable reductions. It's not that we want to decide like case by case, okay, if this type is concerned, then yes, it's okay, but otherwise not. I mean, we want to have a more general picture, I would say. Why, for example, the beta reductions are fine, and maybe certain other reductions too, but others seem to be not to be acceptable. And also, by using such a restriction, what we do basically is to abandon Curry style typing and do a de facto church style typing instead, because this brings me to my second objection, which has been raised. You could say, yeah, well, okay, maybe maybe then the problem lies in Curry style typing. Maybe we should use church style typing instead, where this couldn't happen. So that these features of type reconstruction, that they just show that Curry style typing is disadvantageous, and because they show some kind of looseness of the connection between terms and types here. I mean, my response would be to say, okay, but if we're interested in proofs from a philosophical rather than a merely like technical point of view, then I think there are points in favor of Curry style typing as opposed to church style. To just briefly mention the differences here. So in Curry style, the syntax of terms is independent of the type. So lambda xx, for example, is a term of type a implies a for every type a. Whereas in church style, the types are part of the syntax of the terms. So the type of each variable is unique. And such a term here would be a term of type A implies A, but not of B implies B. So here you definitely get some features which might seem desirable, like that terms are uniquely typed always, and that you have an invariance of types under conversion. Because in church style, all terms are typed, so the beta radixes are type 2, and this restricts beta reduction in a way that type changes are just prevented by definition. But you also restrict yourself from asking interesting questions, like because the typing rules are just part of the definition of the language, cannot be like used to answer questions about a more like primitive underlying language. We cannot ask like, is this term meaningful? Can this term be assigned this or that type? That doesn't make sense in church style. And applied to proofs, these seems to be like philosophically maybe interesting questions. And yeah, with Curry style, we have a language where these questions can be asked. And also, like in church style, the term distinction is, I think, too fine-grained. So in church style, these terms are basically as different terms as, for example, these, which doesn't seem intuitive to me, at least. For me, it's more intuitive to say, okay, these terms do not express something entirely different, but are instantiations of one and the same general concept, expressing the identity function, basically. And yeah, these concepts can be captured in Curry style typing by saying that it's not infinitely many terms expressing identity functions, but one term which can be assigned infinitely many types. The last point is to say, okay, if you consider such a theory of sense and denotation of proofs as I do, of course you don't have to buy it, but for me, this is something like church style typing would yield too fine-grained results here too, because syntax and meaning would basically collapse. We couldn't have a way to express derivations which only differed syntactically. So for example, only in the variables chosen for this formula, but are otherwise identical in sense and denotation. To conclude, I want to say that, okay, reduction procedures for terms must not yield the possibility of relating terms of arbitrarily different types. And in such a framework, we have reductions which are like clearly well-behaved, where subject reduction holds. Then we have some which are clearly non-well-behaved, where weak subject reduction doesn't hold. And we have some in between where subject reduction doesn't hold. And I mean, those need not necessarily be excluded. Then the like concrete philosophical background theory is maybe is the thing that needs to decide whether we buy into this theory of proof identity or not, whether we want to accept these reductions or not. And about denotation versus meaning, the one thing is having to identify all proofs of the same formula, which is surely not a good thing. But this is like a question about denotation. I want to say that, okay, but having to commit to a notion of reductions where terms of a certain type reduce to terms of completely unrelated types, such a system cannot be considered like rule generated anymore, and thus it cannot be considered to be meaningful anymore, which is even worse, I think. And that was it. Thanks a lot for your attention.